Hello everyone, my name is Dr. Mitali Dugvekar and I am Assistant Professor in the Department of Science Chemistry, the Bhopal School of Social Sciences. Today we are beginning with the Chemical Kinetics unit, which includes the determination of rate of reactions. Now if I talk about any chemical reaction, now this chemical reaction, it can proceed with various types or various mechanisms. So if I have to study the mechanism of this particular chemical reaction, I will have to calculate three major things. First is its possibility, that this reaction will occur or not, or its feasibility. So this the branch of science which deals with the possibility or feasibility of this reaction to occur is studied by thermodynamics, chemical thermodynamics. Secondly, if I have to study the extent of this particular reaction, this extent can be studied with the branch of science which is known as chemical equilibrium. And thirdly, the unit which we are going to discuss today are chemical kinetics. Chemical kinetics determines the rate or speed by which the reaction proceeds. So chemical kinetics is the branch of physical chemistry that is concerned with understanding the rates of chemical reactions. Now chemical reactions can proceed with many rates. We can see in our day-to-day life, we can see that there are many reactions which either proceed very fast, which either proceed very slow, or which proceed with a normal time, or which we call as moderate time. So basically there are three types of reactions. First is your very fast reactions. For example, I have taken here the example of sodium chloride and AgNO3, silver nitrate. It precipitates to give sodium chloride and sodium nitrate. This reaction is very fast reaction, or we call it instantaneous reactions. Such reactions occur at just a moment of time or instant of time. Second type of reaction is your moderate reactions. Moderate reactions are those which require quite a measurable amount of time to occur. For example, hydrolysis of an ester. Ester is the functional group which is denoted by RCOOR. Its hydrolysis leads to the formation of a sodium salt or a particular salt of an acid along with an alcohol. And third type of reactions are your very slow reactions which may take many months to occur. For example, rusting of iron. The rust which is developed on the iron is your Fe2O3. So these are three types of reactions which basically proceed by different rates or different speeds. Now, if I have to calculate the speed or rate of a reaction, how can I calculate it? So, see, first is the graph. This is the first graph which is denoting your time is on your x-axis, whereas your concentration is on your y-axis. Concentration means what amount of reactant or what amount of products are being utilized in this time. So, we can see that as the reaction proceeds with time, or as time proceeds, the concentration of reactants reduces as time proceeds, whereas as time proceeds, the concentration of products increases. So if I have to calculate the rate of appearance of products, so I can calculate it by the slope of the particular curve of products with respect to time, which means dC by dt will give me my speed of the reaction. Secondly, if I have to calculate the rate of disappearance of any of my reactant, so its slope or its curve in which it is depicting here also in the second graph also, in the y-axis I have taken the concentration, whereas in the x-axis I have taken the time, which means that how fast or how slow the reaction is proceeding, it is utilizing or it is reducing its concentration of various reactants or products with respect to time taken. So if I have to calculate the rate of disappearance of reactant, I will calculate it by the curve of this particular reactant. The slope of this curve will give me the rate of the particular reaction. Now, how can I express the reaction rate in any reaction? For example, this is your reactant and this is your product. Now, I have to calculate the rate of disappearance of R. How I can calculate it? Negative delta. Delta means change in concentration of reactant upon delta time, means change in time. Initial time, final time. Final concentration, initial concentration. Now, why I have included this negative sign over here? This is because we have seen that as time passes, concentration of reactants, what happens? Reduces. Which means that concentration of reactants final is less than concentration of reactants initial. So, if I put these values in this particular rate of disappearance of R and I omit this negative sign, suppose. So, what will happen? Concentration final minus concentration initial upon time taken. But this will be a negative quantity. Why? Because concentration final is less. Anything a smaller number cannot be subtracted from a greater number, it will lead to a negative sign. So I will obtain this negative sign. But rate of reaction can never be negative. You cannot find a rate of reaction where it is negative in nature. Like whenever you ride a bike, if you go reverse, you do not get a negative speed. You have a positive speed only. Similarly, the rate of reaction can never be negative. So in order to remove any kind of discrepancies, we have included a negative sign over here, which means that this negative and this negative will get cancelled, and overall the rate of reaction will become positive. Now in terms of products, rate of appearance of products, there will be no negative sign. Why? Because it is as obvious that with the time the concentration of products increases. It does not decrease. So there is no question of negative sign. Secondly, I have taken an example of NH2 plus 3H2 gives 2NH3. This is a very famous Haber's process. Formation of ammonia. Formation of ammonia. Now, if I have to calculate the rate of disappearance in terms of N2, how I will calculate? Minus change in concentration of N2 upon time taken. If I have to calculate the rate of disappearance in terms of hydrogen H2, minus change in concentration of H2 upon time taken, and rate of appearance NH3, no minus. Why? Because it is a product. It is not reducing, but it is increasing as the time is proceeding. So change in concentration of ammonia and time taken. Now, we saw that there are certain numbers, 3, 2. What are these? These are known as your stoichiometries. Stoichiometries of a particular reactant or a particular product. So when I am calculating rate of disappearance or rate of appearance of any single product or any single reactant, I will not include these numbers. But if I am calculating rate of reaction of this whole, then these numbers have to be taken into account. How? We will see. Now, I have written this particular analogy, which means, what does it mean? It means that the rate with which nitrogen is disappearing, hydrogen is disappearing thrice more than that rate. Means if one molecule of nitrogen is disappearing, 3 molecules of hydrogen are disappearing. So that's what I have written here. So when I bring this 3 from this side to right hand side, that is from left hand side to right hand side, it takes the form of 1 by 3. And if I talk about the analogy between nitrogen and ammonia, same over here. The rate with which ammonia is being formed is twice greater than the rate by which nitrogen is being reduced. So, when I bring this 2 from left hand side to right hand side, it becomes 1 by 2. Now, overall the rate of this reaction, when we write about overall rate of reaction, it will be equal to dN2 upon dt with a negative sign, which is equal to negative of 1 by 3. How 1 by 3? From here, dH2 means the change in concentration of this particular reactant, which is further equal to, now no minus, plus 1 by 2, change in concentration of ammonia with respect to time taken. So this will be my overall rate of reaction. And rate of reaction can be calculated by just this, or by just this, or by only this, provided you have to include the stoichiometries given. But if rate of appearance or disappearance is being questioned, then no role of stoichiometry comes over here. So this was your how you can calculate the rate of a particular reaction, or how can you express the rate of particular reaction in terms of decrease in concentration of reactants or in terms of increase in concentration of products. Now there are few factors which affect the rate of a particular reaction. For example, your first factor is your nature of reactants. Ionic reactions proceed generally faster as compared to molecular reactions. Second is your concentration. Now, how does concentration affects the rate? Concentration of reactants means the number of effective collision will increase the rate of reaction. Means all the reactant molecules which are colliding together won't lead to the formation of products. Only there are certain type of collisions which are known as effective collisions. If those happen then only it can lead to the formation of products. So more the concentration of reactants, more is the frequency of these effective collisions, and more is the formation of your products. Third is your temperature. Generally, as the temperature increases, the kinetic energy of reactants increases, which in turn increases the effective collision, and which in turn increases the rate of the reaction. Catalysts are those substances which alter the rate of a particular reaction. It can also increase or it can also decrease without being involved in that particular reaction. Surface area. This particular point is applicable to only solid reactants when the solid reactant is converted into powdered form. So it leads to an increase in surface area. More surface area means more frequencies of collision to occur. So it will lead to more formation of products. And third is presence of light. Now there are certain reactions which proceed only in the presence of light. These are known as photochemical reactions. So in case of this, the light has altered the rate of a particular reaction. Now, order and molecularity. There are certain other, these are some more important terms when we talk about the rate of any reaction. Now, it was said that if I have this particular reaction, A moles of reactant A and B moles of reactant B react to give C moles of product C and C moles of product D. Now, it was proposed that rate of any reaction is directly proportional to concentration of reactants raised to the power, raised to its molar concentration or raised to its stoichiometry. This is your law of mass action. So, according to law of mass action, rate of reaction will be directly proportional to the concentration of reactants. As rate of reactants will increase, rate of reaction will also increase. Now, if I have to remove this proportionality sign, I will have to include a constant. And this constant is known as your rate constant or velocity constant. Rate constant. Okay. So, this is your according to your law of mass action. But there was another proposed theory of the rate law. Rate law states that in writing the rate of a reaction, the raised to the power which we are writing is not necessary that it will be the stoichiometry only. It will be raised to the power of those moles of reactants which are actually participating or which are actually colliding to give products. So, it will be alpha plus beta. This alpha plus beta is nothing but your order of reaction. So, order of reaction is the sum of coefficients of power or powers of the reacting species that are involved in the rate law equation. Means the number of moles of reactants which are actually colliding to give products. And this is an experimental quantity. You cannot just view any reaction and take out its the results that what might be its order of reaction. If it happens that it is just a coincidence, that suppose it is coming that 1 mole of NH3 is decomposing to so and so reactants. So, and order of this reaction is also 1. So, it is just a coincidence. It is not necessary. This stoichiometry is also your order. It is just a coincidence. So, there are various reactions which are like zero order reactions, first order reactions, second order reactions. So, an example of zero order reaction which I have taken over here is combination of H2 and Cl2 to give hydrogen fluoride. Here, zero order means the rate of this reaction is not dependent on either of any reactants, not on H2 and not on Cl2. And decomposition of nitrogen, nitrous oxide to give nitrogen and oxygen. This is also an example of zero order reaction. Now, if I talk about examples of first order reactions, these all are those reactions whose rate of reaction is dependent on the concentration of only one reactant. Right? Second order reactions, those reactions whose concentration, the concentration in terms of rate of reactions is dependent only on the concentration of two reactants. Order of reaction can even be fractional or it can also be zero. Now, molecularity. Molecularity is nothing but your the actual number of effective collisions that take place. And it is just important in case of your elementary reactions. Elementary or single step reactions which proceed by a single step. So, there are various types of reactions like there are some single step reactions which are known as elementary. There are few complex reactions which proceeds by many steps, multi-steps. So, in case of multi-step reaction, the slowest step will determine your molecularity. So, molecularity and order are very different from each other. Order of reaction is an experimental quantity which can be determined only experimentally, whereas molecularity is the number of collisions between the reactant molecules which are taking place to lead to the formation of products. Secondly, it can be 1, 2, 3, 0 or even fractional, but molecularity can be 1, 2, 3 only. It cannot be fractional. Why? Can you imagine of a case where half of the molecule is reacting with another half of a molecule? No, it is not possible. So, molecularity can only be 1, 2 or 3. Order is an experimental, whereas molecularity is a theoretical quantity. Order is applicable to elementary as well as complex, whereas molecularity is applicable only in case of elementary reactions. And similar is the case with your order of reactions in case of your complex reactions. So in this module, we studied about the rate of reaction, how can it be expressed in terms of decrease in concentration of reactants and increase in concentration of products. We saw about the terms like order of reaction, molecularity. In the next module, we will study about the integrated rate law equations for zero, first and second order reactions along with calculation of its half-life. That's all for today. Thank you.